the surface. Because then it would be the bar and the pulley that's connected to the surface.
Yeah, the bar, technically the bar is touching the
Pulley?
The bar is touching the pulley. Is the pulley the whole contraption or pulley just the wheel?
That's what I'm asking.
And are we not just treating the pulley as if it were part of the ground?
That's what I was hoping to get to.
Pulleys,
Yeah,
yeah.
that's what I was gonna say.
Oh, well.
I was gonna say, here, I didn't put a check mark there, so there's no way it's like.
When I wrote this up here, I have the pulley attached to the ground right here, so you don't need to worry about the forces here.
We're assuming that it's not gonna, like, be freestanding or something like that.
Right, if I wanted you to address the forces specifically on the pulley, or say between pulley and ground, I would have drawn the pulley as a separate object.
Okay.
So on the complex diagram, I split it apart for you, just so you're not debating what to include. Some students will include the forces between the pulley and the ground, even though I have them attached.
Ignore.
Exactly.
So on the test, you already have this split up for us. Is that correct? Or are we drawing it split up?
Oh, on the test level complex force diagram problem,
Yeah.
I set up the scenario, I draw the picture with everything touching, and then on the next page, usually, it's all the different objects already split apart.
Oh, that's helpful.
Yeah, because I originally, when I first started doing those type of questions, I didn't do that, and then I noticed students couldn't read my mind about how to split the objects up. I'm assuming your mind reading skills are about on par with theirs.
Maybe a little above average, but I don't want to put that to the test.
Okay. We don't know on that day what it's gonna be like.
Right,
Okay.
yes.
Gravitational force.
We've got it on, box 1 in the ground, so it's acting down, and then on the ground it's acting up. Same for box 2. And then should we assume the same thing for the pulley or not, because it's like the ground?
Pulley's part of the ground.
Okay.
I could have just as easily drawn a bit of earth right here. It's frictionless, so it's not like, I call it a pulley, but it's just gonna sit there while the rope slides over it. There's nothing to cause the pulley to turn.
Are we assuming that the rope doesn't have any gravitational force?
That's the massless thing.
Gotcha, okay.
But again, if you put down the weight of the rope,
Then it would have gravity.
yeah, I would ignore it.
Okay. Well.
Any questions before we get to the next level of complexity?
So when we deal with something, the way we can know how to ignore it is if it feels insignificant, but like, I know you said you'll break it up for us, but,
On the complex diagram,
yeah,
the rope will have tension at each end.
okay,
That's it. for the
that's
rope.
it. And then,
Pulley, for the complex diagram, I've always had the pulleys as part of either the ceiling or the ground.
okay. But in actual physics, like in an experiment, we would want to try and include as many forces as possible.
Without going insane.
Okay.
That's one of the reasons why we use the super pulleys. This group has done the super pulleys, right?
Yeah, we
Okay.
did, with the force table.
Super pulleys, one, there's not much mass to them, so and also there's no friction at the bearing,
Yeah,
wow, that was an exaggeration there.
yeah.
There's not much friction at the bearing, so ignoring it does not have a major effect.
Okay.
Yeah.
I am still struggling with determining the net force or the resultant with all of these, because it seems like everything has its equal and opposite, arrow.
The classic,
I mean, like
Force
box
and
falling
fair
at the simplest has, the weight pulling down and the weight pushing up, but the box itself is in fact moving. And someone asked that question about the pulley system too, like it seems like it would be moving.
we're not looking at the net force of the entire structure.
Yeah.
Because in which case, if we're looking at everything as one bit, these would all be considered internal forces, and the net force would be 0.
Right.
You cannot have an object force itself to move without touching something else. When we actually get to the analysis piece of it, what we're gonna do is we're gonna concentrate on these right here. So if we try to figure out what is the acceleration of mass 1 and mass 2, actually, let's just run through a problem. This is probably one of the simpler ones, so we'll run through it.
Okay.
So, whether it answers your question or not, we'll find out. We did the force diagram.
Oh. Crack a disc.
Direction of acceleration. If one accelerates, which way is it going to accelerate?
Down.
Yeah. This is the point where you have to use some common sense of going, all right, there's no way that mass 2 is going to go shooting off to the left and mass 1 is going to go up. There are situations, and we will get to them, where you can't tell what's going to happen. There's no way to know. You take a guess, and what you get for acceleration will determine, oh, I guessed it correctly, or I guessed it wrong.
Yeah.
So this one's down. Now, this arrow I'm drawing down here with acceleration, this is not part of the force diagram. This is just a little note saying that's the direction it's going to go. And then which way will mass 2 go if it accelerates? Okay? Now, notice I don't put a subscript next to either of those A's.
Because the acceleration is the same.
The magnitude is going to be the same. I guess technically the vectors are different, so let's get rid of that vector symbol. They will have the same magnitude of acceleration. Part of this is under the ideal rope that's stretchless. When mass 1 moves, mass 2 is going to move right with it. It'll cover the exact same amount have the exact same magnitude of displacement in the exact same amount of time. For the sake of simplicity, at this point, I'm going to give it an initial velocity. Initial speed of, you know what, really don't care what the value is. Its initial speed is greater than 0. And then, as a sneak preview of what we will get to eventually, mu sub k is equal to we'll make it 0.4. I'll talk about what mu sub k means in a moment, but that is not the letter M. It is not the letter U. It is mu, it's a Greek letter. I think we've covered mu's in this class already? Or is that the other one?
I don't think we have.
Okay.
Maybe for units.
So the way you make a mu is you draw a letter U, and then you put a stem up front. I've seen some people make them look more like M's. It gets very confusing when I'm going, you have a mass here?
Yeah.
Does it have units?
No, it has no units. This is known as the coefficient of kinetic friction.
I'm just glad it's not K.
Yeah, really.
The coefficient of kinetic friction, and a spoiler alert for something I'm going to ask, hopefully before fall break. It's dependent upon the two surfaces. It's found experimentally. The essence of the experiment to find it is you take a surface, a known surface, you put it at an angle, you put an object onto it, and you time how long it takes to slide a certain distance, and you calculate. In essence, you'll calculate the friction that had to have been there in order for it to slide at whatever acceleration it was. All right, so the coordinate axes. We basically have two for mass 1, it's a one-dimensional problem. I have only forces that are vertical. For mass 2, I have 2 dimensions. So I'll end up with 3 equations of motion, which is this part right here. But when you're doing the coordinate axes, you don't have to have the same coordinate system for each mass. Matter of fact, it's rather convenient in this case that we make down positive here. And for this one, to the right's positive. We'll call this I2 hat. And I'm going to call this, I'm going to call it I1 hat. If you prefer J1 hat, that's fine too.
Now, it doesn't matter if I make up positive or down positive here. But typically, you're going to make one of your positive axes in the direction of acceleration, or in some cases velocity, but in the direction of acceleration in this particular case, and the other one here is going to be perpendicular. So, up or down positive.
Oh, down, wait.
I heard up first.
Okay, yeah.
So you're saying there's a right and wrong with the I hat directions being positive, because you want them in the direction of acceleration?
Yes.
Okay.
I want them in, but this, the perpendicular one, I don't, up or down. So that's the coordinate axes. Decomposition. The decomposition phase is we look at all the vectors that are involved in our two masses here. Are there any forces that are not in the positive or negative I hat direction or positive negative j hat direction?
Force or friction?
Friction's in the negative I2 hat.
It's the,
Tension.
normal force between the rope and the pulley, right?
Okay, if we were including the rope into this, then yes, absolutely, but we are not.
Okay.
We're leaving the rope out of it. Just looking at these two masses right here.
No?
All right, yeah. So there's nothing to decompose, so nothing to do. Equations of motion. Now, part of the issue that some students run into in equations of motion is that we just spent 2 chapters going over motion. Equations of motion does not involve those formulas, does not involve any of the cake, or even non-constant acceleration. Equations of motion are independent of those. Equations of motion are based upon the fact that force is equal to mass times acceleration. Again, Lorraine, have I done F equals MA before with this group?
I don't think so.
All right.
I've already known about it, but I don't think we've really covered it in this class.
Classic bedtime stories when you're growing up, F equals MA.
Oh, yeah.
I'm sure all of us had those stories.
No, it's
yeah.
not.
Thinking how badly I work my kids by telling them physics stories. All right, anyway.
Did you actually?
I used to, especially my son, I got really tired by the time my daughter was born. But yeah, the story of quantum lions, you know, a lion jumps through a window and ends up going through 2 windows at once and then reforming. It's,
You just like pounded this into his head, like, question everything, like, this is physics.
yeah, there's a certain amount of that. My son in 2nd grade, when they were going over, the teacher said, was talking about Newton's 2 laws of motion, and my son raised his hand and said, aren't there 3?
Yeah.
All right, what this is saying is that on my left-hand side, I'm gonna have forces, on my right-hand side, I'm gonna have mass times acceleration. So, we'll take, this is gonna be the I1 hat equation. Do not put an equal sign after this. Some students love putting equal signs. I'm gonna do this. All I'm doing right here is just noting this is the equation that comes from the I1 hat equation. So when you do it, we've established our positive direction right there. What are all the forces in the positive I hat 1 direction?
Acceleration.
Not a force.
Gravity, tension.
Weight.
Weight. Okay, so we have weight. Any other in the positive I1 hat direction?
The force of tension.
Are we counting that?
That's not in the positive.
Oh, because it's.
All the forces in the positive I hat direction. That's it. Minus. What are all the ones in the negative I hat direction?
Tension.
Are we only looking at the box?
Yes. Only
Oh, okay. All right, gotcha.
more support for the lack of mind reading skills. Equals, I usually don't put the parentheses there, but. Equals, I have only 2 forces acting on box 1, so I have only 2 forces on the left-hand side, equals mass 1 times acceleration. I don't need a subscript here because, well, the acceleration of my 2 objects is the same. I have had some students do put subscripts here and then later on say, well, A1 equals A2. Sure, if you wanna do it.
Kind of a goofy question, if you had the two boxes suspended over a pulley and they were both, like, well, they couldn't both accelerate down. Never
I
mind,
hope
we
they
would
don't.
never have the vector symbol over the A in this case, because the acceleration will always be in different directions, is that right? We're just using the, like, scalar A?
Yeah, the magnitude, I hesitate to say always. But on the problems where we actually calculate acceleration, I think I've had only one test problem where there were two separate accelerations going on at the same time. Where you actually have to solve for an acceleration. And then I've got an I2 hat. I know we've just done one example. Anyone want to take a shot at the second equation?
Yeah. Positive is, force tension. And then you've got, well, that's it for positive.
Okay.
J hat, oh, we're only high hat, so negative is,
Friction?
friction.
So you go to M1.
There, I might have misheard, but
I thought it was.
M2.
M2.
Oh, sorry.
And then we have the J2 hat equation.
So the Y2,
Minus weight. Is this also equal to M2 acceleration?
Is
No.
that 3?
M2 times, what is the acceleration?
Oh, G.
zero, is it
Zero.
zero?
0. It's
Oh.
not accelerating up or down. The thing we've already established is accelerating to your right.
So wouldn't this just be 0? Yeah.
Yeah, at some point, we'll just skip over the mass 2 times 0 and just go straight to 0. One of the reasons why we pick our coordinate axes so that one of them is in the direction of acceleration is so that the other one has no acceleration at all. I want one of the equations to be equal to 0.
So, hold on. Wouldn't we just completely ignore J hat? Because there would be no, Y2 minus weight 2 would equal to 0, right?
Yep.
Okay.
We do need to worry about it, and we'll get to that in just a moment.
Okay.
I generally do a slightly different progression here. By the time we get to that progression, in the typical progression, you'd be going, oh, yeah,
Yeah.
I see what we did. But I'll bring it in just a moment.
Yeah, for I had 1, so you had weight 1 as positive, but how would it be positive if it's going down?
Because we said down was positive there.
Oh, okay, and for, so then up is, okay, so that explains why the tension would be negative. Right?
Correct.
It's negative.
Yes. And one of the other things I wanted to emphasize was that my coordinate system for each mass does not have to be the same. Some students want one coordinate system to cover everything. Here, when we're done with this, if I remember, I'll go through at least setting up the equations if you do want one coordinate system to cover everything.
Wait, and also, why would why would the weight and force tension, wouldn't that deal with J hat, because
It's vertical.
Yeah, it's vertical, it's not.
I could have just as easily made that J hat. I have to be the acceleration direction, but that's my own eccentricity, one of many. Yeah, there's nothing wrong with picking J that, but I don't want you to get into this thought that I hat has to be this way, J hat has to be this way. I hat is whatever direction I say it is. J hat's whatever direction I say it is, as long as it's perpendicular to I hat.
Okay.
When we get to the box on ramp, it becomes very clear, I hope, why we don't want to do horizontal vertical for an object that's moving diagonally.
We did box on it, and you said it's so that we can like adjust the.
Yeah. Any other questions right now? All right, substitution, that's the first S right here. There are certain formulas that we have for certain things that are independent of this, that are not problem specific. There's a formula for weight, and there's a formula for friction. So later on, we'll introduce a formula for centripetal acceleration, acceleration while traveling in a circle or around the curve. The formula for weight comes straight from this equation right here. I think you've already.
Yeah, we talked about it for a second.
Weight equals mass times gravity. No.
I get.
What have I done?
What did she say that was off?
Weight is force, should be.
It is, that's not the problem.
Mass times acceleration due to gravity. Yeah, when you say just gravity, gravity's already a force.
Ooh.
Or gravity's already got a, what, we said.
Gravity is a huge topic.
Yeah,
Yeah. Force, there's force due to gravity, there's acceleration due to gravity,
Yeah.
there's gravitational constant, there's a lot of little bits that go within this huge category of gravity. That's my problem.
right, so our force is already gravity's weight, or the weight of gravity, but in here we're using acceleration due to gravity.
Which is a G.
Yes, yes.
Okay, alright.
So weight is equal to mass times acceleration due to gravity. Weight of gravity sort of mixes two things. It's force due to gravity or weight. And then friction, kinetic friction, in this particular case, because I said it's moving, is equal to mu k times y. I'm not offering any justification for it at this point, I'm just sort of throwing it out there. In mild justification, normal force, the higher the normal force is, the more that something's pushing back. And so you can think of normal force as an indication of how tightly two surfaces are pressed together. The more they're pressed together, the greater the friction. So my formulas now become M1G minus tension is equal to M1A. Tension minus mu Ky is equal to M2A. And I'm going to do two things at once over here in the third equation. I'm going to make the substitution, and I'm just going to go ahead and bring weight over to the other side. Ooh, this should be Y2.